Okay, using the sine rule. Remember, this is not SOHCAHTOA, the sine rule. It's A on sine A equals B on sine B. So if you were to use the sine rule here, remember we look for pairs of opposites. So am I finding a side or an angle? I'm finding the angle. So I would go, remember, I always put what I want first. I go sine theta over, remember, it's opposite. What's its opposite? 9 equals sine 21 degrees over 6. Okay? So here I'm finding, I'll just write here, find theta. Okay? So this is what we've done so far. We've gone, remember the sine rule is the following. Remember we've got A over sine A equals B over sine B, or we can flip it. Sine A on A equals sine B on B. If I'm finding the angle, I use the sine angle over the side length. Do you remember that? All right, so what do I now do if I want to find sine theta? On its own, it's sine 21 degrees over 6. What do I do with this? Times 9. And then I get sine theta equals, can someone work out what that is, please? Just not the actual angle, just work out what sine 21 degrees over 6 divided by 6 times 9 is. So when we do this, okay, the thing is that sine theta equals 0.5375. This is a positive number here, so sine theta is positive. In which two quadrants is sine theta positive? Just think of the curve. Quadrants 1 and 2. So what I do, I first work out my acute angle just by doing, that sine to the minus 1 of that. So keep that answer in there and just do it as you would normally do it. And what do you get? So what did you get? 32? All right, 32 degrees. All right, so 32 degrees. So girls, the question might be, you know how I've got find theta? I might say to you, find theta. Girls, do you think, if this is 21 degrees, and if this is drawn to scale, if it's drawn to scale, this one would be pretty small. This has to be obtuse. So we will, if it is obtuse, we'll say to you, find theta if theta is obtuse. Okay? Because doesn't it look like it's going to be obtuse? You don't normally look at it and just say that looks obtuse. We will ask you, find theta if theta is obtuse. So this is the acute angle. If theta is acute, it would be 32.
33.
Oh, someone said 32.00. All right, so it's 33 degrees, yep. So girls, if theta is obtuse, that's quadrant 2. Isn't it 180 minus? So therefore, if theta is obtuse, you just do 180 minus that angle. Remember the little butterfly, look, 33. If you're in quadrant 2 and it's obtuse, the angle's going to be like that, all the way to there. So it'll be 180 minus 33, which is 147 degrees. Do you think, so if I tell you theta's obtuse and you get an acute angle here, remember for quadrant 2, for obtuse angles, quadrant 2 is from 90 to 180, isn't it? That's an obtuse angle. Quadrant 2 is where your obtuse angles are. Because look, watch. Isn't that an obtuse angle? If that's my axis, isn't this an obtuse angle?
Yeah.
You know how I go 0, 90, 180? That's an obtuse angle. So if you want the obtuse angle, we're talking about quadrant 2, and quadrant 2 is always 180 minus theta. That's how you represent an angle in quadrant 2. So the reason we didn't do this before, we had to do our sine curve, cos curve, tan curve to be able to do this. See how I've got sine theta, again, is positive 0.5375 coming back here. That means that sine theta is positive in quadrants 1 and 2, and that's why we can work out the obtuse angle in quadrants 1 and 2. Sorry, the obtuse angle in quadrant 2. So when you do it on your calculator, girls, whenever you do these things on your calculator, you'll only ever get the acute angle on your calculator. It doesn't give you the obtuse angle, all right? So you'll get the acute angle on your calculator. If they tell you find theta if theta is obtuse, you need to just do 180 minus your answer to get an obtuse angle. All right? You can clearly see in this diagram that theta is not 33 degrees. It's bigger than 90. Okay? This is 21. This looks like about 30 or something like that. And that here we're getting is 147. I'm going to do another one. So here, so again, find theta if theta is obtuse. So we've got, let's look for our opposites. So it's only for the sine rule, girls. This is not for the cosine rule, okay? Because cos is negative in quadrant 2, all right? So what do I do? Sine theta over, what's it? 16 equals sine 47 over 12. Sine theta equals sine 47 degrees over 12 times 16. You can get an answer, and then you can work out theta acute, and then you can work out obtuse angle theta. Okay? 0.975, whatever it is, dot, dot, dot. You know, to find theta, don't we go shift sine of that answer? So we've got, therefore, sine theta is sine 47 degrees over 12 times 16. When we evaluate that on the right-hand side, we get 0.975. Notice it's positive. Sine theta is positive 0.975, meaning that, you know, I can give an acute angle answer and an obtuse angle answer. The acute angle is just sine to the minus 1, and we get 77 degrees is my acute angle, and my obtuse angle will just be 180 minus 77, which is 103 degrees. See, you can clearly see that this is not going to be 77. It's bigger than 90 degrees. Okay? That's how you do that. Pretty simple. So once we've learnt about sine, looked at the sine curve, and know that sine theta is positive in quadrants 1 and 2, this now makes sense to do this. Okay? The sine rule is used for non-right angle triangles. Do you remember that the sine rule, so the sine rule is used for non-right angled triangles. Remember the sine rule is this, A on sine A equals B on sine B, etc. Or we can do the flipped version of it. What happens if we use the sine rule in a right angle triangle? So you're not meant to use it in a right angle triangle. If you've got a right angle triangle, girls, you only use Pythagoras in a right angle triangle or SOHCAHTOA. Sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. And tan theta is opposite over adjacent in a right angle triangle. So sine rule is used for non-right angle triangles, but let's say you had a slip up and you decided that you're going to use the sine rule in a right angle triangle. It'll still work, just gets a bit long and messy. So I might say to you, no, that's a right angle. Okay. Now this is a right angle triangle. You should recognise it as a Pythagorean triad, 3, 4, 5. But let's say I want to find the size of angle theta, okay? So, you know how that's opposite here? See, really what I should be doing is using, I really should be using what? What should I do? No, if I want theta, what should I do? What should I do? I should do SOHCAHTOA, and I should go sine theta is opposite over hypotenuse. This is what I should do, right? Sine theta is 4 over 5. Do you get it? And then you work it out. Can someone work it out? Sine theta is, please just give me the acute angle. I'm not saying it's obtuse. I mean, we're not using sine rule, any the other sine rule. But what do we get for here? What is the size of that angle? So this is a right angle. This is theta, that's 4 and 5. Is that to the nearest degree? 53 degrees. Now let's say you got all confused and you used the sine rule for this. If you use the sine rule for this, remember we look for pairs of opposites, and I want this theta, and I go sine theta over what? equals sine what? What angle is this? Sine 90 over 5. Does anyone know what sine of 90 is? 1. And you're going to see, so I go sine theta is sine 90 over 5 times 4. Now, I know that sine 90 is 1. Aren't I just solving exactly the same thing? Okay, and that's what will happen. If you use the sine rule in a right angle triangle, you'll go, and I don't want you ever doing this, but you go sine theta over 4 equals sine 90 over 5. Well, then I rearrange it, and the inverse operation of divide by 4 is times 4. But sine 90 is actually 1, okay? And I've just got sine theta is 4/5, so you'll get theta is 53 degrees as well. So it just shows that if you were to use the sine rule, it would, in a right angle triangle, you'd still get the same answer, but why do that? It takes so much longer, all right? Of course, you would use sa, ka, toa, because it's a right angle triangle, okay? Don't go and use sine rule. Don't use the sine rule. But it would work if you did. The same thing would happen. This is a right angle triangle. Remember, you've got two formulas now for area of a triangle. We've got area of a right angle triangle from, year 7. What's the area of this triangle? Area equals half times the base times the height, which is a half times 3 times 4, which is 6. I'll just go units squared, so I don't know what the units are. But what happens if you use the area of a triangle rule, which is this one, half AB sine C? Do you remember that? For non-right angle triangles. So if I use, so that's how we normally do it. That's how we normally do it. It's a right angle triangle, half times the base times the height, okay? But if I use the new rule that I've learnt, area of a non-right angle triangle is a half AB sine C. Remember, it's two sides and the included angle. So what's going to be AB? Which one's C? Do I have two sides? Remember, for area of a non-right angle triangle, you need two sides and the included angle. So capital C is there. There's little c, which I don't need. There's little a, there's little b. You would never normally do this. I'm just showing you that if you did, but I don't want you to ever do this. I'm just showing you that if you did do it, what would you get? A half times, what's A? So there's capital C. You need two sides and the included angle. So I'll call capital C my angle. So little c is opposite. These are A and B. It doesn't matter the order, okay? So what's my little a? And my b? And my sine of 90. What's sine of 90? Sine of 90? Thank you. Is it the same? 6. So if you mistakenly used the area of a triangle rule, the new one, for non-right angle triangles in a right angle triangle, it's still going to work if you've got that type of right angle triangle. All right? But I don't want you doing it. Just showing you that it works. That's all. All right? I mean, this works, but you wouldn't do this because this is a right angle triangle and you would use half times base times sine. But when you do use it, because sine 90 is 1, you'll get the same answer.